Good afternoon now. I'm Sarah Christoph. I'm a software engineer at Nscale. Thank you. A fun fact is a long time ago, I worked at a small DevOps company. They build like cloud tools, and they invested heavily in my public speaking. And I've never practiced any of the things the teacher taught me until today. So if I'm speaking really slowly, you can blame HashiCorp. And if I'm speaking really well, you can thank me. So I'm about to talk about the dining philosopher's problem. It's a problem that's taught in college to teach concurrency to students. I'm a 3-time dropout, so I never paid to learn this problem, but I taught it to myself just so I could learn cool things that people learned in the 1970s. And after this, I hope you understand it. So I'm mandated to have a slide that says AI in it so this can get paid for. So when thinking about concurrency, like AI, it's big, you run a lot of models, it causes a lot of strain on resources, something deadlock, and my coworker's gonna take a photo, and we're good, cool. Just so everybody knows, I'm a notorious AI hater because I have like trust issues, so ChatGPT and I don't get along. So that's all the AI stuff in this talk. Cool. In the year of 2025, we have a lot of problems with concurrency kind of solved by the layers we're using. In Go, we have mutexes that handle locking. We have like routines that communicate between themselves, that kind of stuff. But this doesn't really cure all of our problems with concurrency, as I'm sure many of you are aware. And so as I was looking up like widespread enterprise issues with concurrency, I stumbled across this paper from Uber. We'll say that my sister works for Uber, so this is not a sponsored talk by her, which means I can't totally shade all of the work done here. But this paper was discussing leaks in Go routines. Basically, it wasn't even full deadlocks, it was partial deadlocks. So what was happening is these Go routines were running, and they'd just kind of not, they'd be like channels that were waiting forever and holding all of these resources. And it kind of begs this question, like if the creators of Go routines or if the Go maintainers had kind of looked at the dining philosopher's problem that we're about to cover, would this have happened? Would Uber have spent a bunch of money having these like partial deadlocks? So we're gonna jump back to 1965. Fun facts about 1965, as I'm sure you're all hoping for. 1, the Vietnam War started in the United States. 2, Tokyo becomes the person who clapped for the Vietnam War. Great job. My father. Tokyo becomes the largest city, surpassing New York, and I live in Holland right now. I cannot speak Dutch, so everyone please give me some help with this. But it is E.W. Dijkstra showcases the dining philosopher problem in his, is it good? Thank you. One person from the Netherlands is here today, and we appreciate it. So, and he debuted this, this problem in his classes just as a way to teach it. And so we're gonna walk through some philosophers. This is just a fun way for me to talk about some philosophers I learned about. And so our guests for dinner tonight, we have, and again, multilingual names, so bear with me. We have Jean-Paul Sartre, which is a French philosopher who was a key figure in existentialism. He's also a Nobel laureate, which I think I said that word in English, right? We have Immanuel Kant. I wanted to make a name joke here. I feel like I'm gonna get kicked off the stage if I do, so you can kind of guess what I want to say. He's a German philosopher who's one of the most influential figures in Western philosophies. We have Kierkegaard, who's a Danish philosopher who's thought to be the pioneer of existentialism. I thought I was that, but he kind of took it from me. We have Jacques Derrida, another French philosopher, whose actual philosophies has influenced a lot of literature and architecture, which I think is kind of cool. And then last, we have Husserl, an Austro-German philosopher. We always have to keep one of those in here. And he established transcendental philosophies. All right, now into the tech stuff and not the cool philosopher stuff. So this is easier to explain with chopsticks than forks, even though the initial thing was forks. And basically, to use chopsticks, you need 2 chopsticks. But the problem we're having is we have 5 philosophers at dinner, and each philosopher is only getting 1 chopstick, which means we can only have, right now at dinner, 2 philosophers eating at a time. Not great. A philosopher can be in one of 3 states: thinking, eating, or sleeping. If he's eating, he's not thinking or sleeping. If he's sleeping, he's not thinking or eating, and so forth. A simple solution to this problem would just only to have 2 philosophers eat and the rest can starve. And that is resource starvation. So we want to avoid that. So we want each philosopher to have a fair amount of food. An important thing to note here also is the philosophers aren't allowed to talk to each other. They need to either be thinking about philosophy, sleeping about philosophy, or eating about philosophy. So the problem we're trying to solve here is we need to satisfy one of the 4 conditions that introduce deadlock. That's mutual exclusion. So basically, no chopstick can be held by multiple philosophers at the same time. This is kind of solved in the bakery problem, if you've read that by Leslie Lamport, where it kind of covers critical code execution. So basically, critical code execution is when you're writing to data. You can't have multiple writes happening at the same time. Mutual exclusion is supposed to help with that. Resource holding. So basically, a philosopher can't hold all of the chopsticks and everyone just be waiting for him to give them the chopsticks. No preemption. So you can't have a philosopher grabbing chopsticks out of other philosophers' hands. Not a fun dinner. Or circular wait. So everyone is waiting for the philosopher on their left to finish eating, and they're just hanging out waiting. So we have a couple solutions we'll cover, and then we're going to go back to the Uber paper. One is Dijkstra's own solution. So he uses a mutex, a state variable. This is a lot of code that you can just look at while I explain it to you. But basically, he has a mutex, a state variable, and a semaphore per philosopher at the table. Now, his solution is focused on negating resource holding, where one philosopher, as I said, may only be holding the chopstick at a time at critical execution. So he negates resource holding by keeping track of the philosopher to the left and the right. So basically, if I'm a middle philosopher, and there's dudes here, and I'm like, hey, yo, I'm hungry. I ask the guy to my left, can I have a chopstick? He's like, I'm eating. Okay, that sucks. Now I'm gonna ask the guy to my right, can I have your chopstick? He's probably not eating because in here we actually hard code the state to 5, but we know that it's pretty unlikely that both people on either side of me are eating. So I can grab a chopstick from one side of me at either time, and it ends the waiting pattern that could happen. Now, there's a couple of other solutions. The reason we like Dijkstra the best is, 1, he created the problem, so he kind of wins. But 2, the other solutions introduce different types of concepts that kind of negate the problem we're solving, whether it's communicating or an external third party. This is the arbiter from Halo. The arbiter solution isn't talking about Halo. It's talking about a waiter, but I like Halo. So the arbiter solution uses a waiter to be in charge of everything. So this is kind of like your, what do we call it now? Like parent-child setup. So basically the waiter is the person who's in charge of knowing who has the chopsticks, who wants a chopstick, and creating kind of a queuing mechanism. The problem with this solution is now we have to communicate with this external third party to navigate like who's eating and when. So it introduces a lot of problems with like, keeping parallelism, or it's reducing speed, right? Because we have to go communicate to this external party, wait for a response, get it back, and then go, okay, now I can eat or not eat. So having this outside person also means like we have to wait for the waiter to come over and hear our request, but also the waiter can sometimes not hear us. So you have a lot of issues with integrating an external third party, as we do in like Kubernetes, with having like etcd and having to communicate and store state, and then waiting a long time for that state to come back. You could implement a wall in this case, and that could also help with speed and parallelism, but obviously this is just a college problem, so they don't implement a wall here. The next is the Shandy Mishra solution. Now, the problem with this solution is that it breaks the philosophers not being able to talk to each other solution. So what happens is it creates a state for each pair. So each philosopher, 1, 2, is a pair. And so for each philosophers at the table that is a pair, there's a number of a chopstick. And the chopstick now, we put states on it. It's either dirty or clean. So when all the philosophers come to the table, all of the chopsticks are dirty. And then it randomly assigns the state to the chopsticks on the table that says, okay, kind of like a heartbeat mechanism, these certain ones are clean. Now, when a philosopher enters the eating stage, they must do so with a clean chopstick. But say we have a philosopher who's entering hungry state and we have 2 that are eating, they will request the chopstick from the ones who are eating. And when the philosopher that wants to switch states and say, I'm done eating, I've met my timeout, I will not hand you the chopstick, they will hand the philosopher a clean stick. So in practice, because this is kind of weird to talk about, basically it's like this. You all show up at a dining table, all the chopsticks are dirty. Randomly, two people will clean their chopsticks and start eating. When someone else gets hungry and say, I'm hungry, you stop eating, you clean your chopsticks, and you hand it to them. Now the cool thing about this is not only is it putting wrong thing. I know how to work a computer. Not only is it putting the impetus on the state of the chopsticks, because of how it handles the resource allocation, it creates kind of like a lightweight DAG. You have all of these different resources relying on each other and like circling back, waiting for each other. So Shandy Mishra problem is the only problem where one, the philosophers talk to each other, but two, all of the chopsticks have their own state, where everything else, the states are only on the philosophers. Okay, now back to the Uber problem. So the fun thing about the Uber paper, read it, I tried read over it a bunch of times because I don't know if you've read a white paper, but you never get it in the first go. So they said they found over 100 Go routine leaks, and they break more into their code. And sometimes you can kind of look at this and say, okay, maybe some of this is like enterprise code practices. They're not following like idiomatic Go. Other things we could blame is Go itself. So they found that a median of 2,000 Go routines are spawned per process. And they're also saying that for Uber, they have like this huge monorepo. And the key characteristics that they had in their problem were specifically they were using a bunch of wrappers to spawn Go routines instead of calling Go itself. And they used a bunch of unbuffered channels. Now they kind of go into a bit of like practices they saw in their code base that were causing these issues. I thought it would be fun just to cover it really quick. So this is a very simple program to show partial deadlock, which is the problem they were seeing. So the compute cost, there, I'd like a pointer. A compute cost gets called, and it calls both get discount and get base cost. When get discount succeeds, and it has to, we hope it does, it then waits to send on the discount channel. But what happens if get base cost on line 11 returns an error? So what happens is then the parent function can finish without our the get discount returning, and then that child will wait to return on a channel that no longer exists. So it would basically, in Uber's case, become forever blocking since there's no longer a receiver if line 11 completes, and then that completes with, or line 11 completes with an error. Okay, and then we have in a select statement, you can open up different Go routines based on conditionals. So basically, if multiple of these evaluate positively, then the runtime picks which conditional to execute first non-deterministically. So the benefit to using this case statement, the select statement, is that with the default, it becomes non-blocking, right? So if nothing evaluates positively, then the default will then execute, and so that means this isn't going to hold forever. However, if you have a select statement with no cases that pass positively without a default, then it will block forever. They also said, hey, we're doing this in a way that is not idiomatic, but it's just fun to point out things that would cause a partial deadlock or something that would block forever. And so to cover this really quick too, in Uber's case, they were using tools for pprof, which is for their instantaneous reports on profiling, and they also use GoLeaks in their CI after this to kind of block more of these happening. And what they found was 44% of their leaks were caused by channels with non-terminating timers. I'm a big timer hater. And another 42 were by for loops which were never closed, which is something I know is in good practice, but I never really thought about the consequences for never closing a for loop. So here is the for loop problem that they proposed. Basically, for loops, Go allows you to iterate over a channel. If you iterate over the channel without causing a close, then the loop will hold forever after going over the final item in the loop. For timers, it's a lot easier. And timers are the bane of my existence. I worked on a project called Raft that was made by HashiCorp. It's the backing of console and boundary, and timers caused like 90% of our test flakes, like something insane. Anyways, it's common for developers obviously to set intervals and using a timer to like flush logs or for evicting cache. So the call to time after here blocks until the message is on the channel. And it basically is the time that's blocking until we get to the endpoint of reporter period. The Go routine kind of works in a cron like this. And they said, even though this is not like the worst thing you could do, the problem is that this wakes up and goes to sleep non-deterministically. Even though it's on a timer, you want to handle the entire life cycle of the request. So instead of having it like this, you would move it into a case statement, and then you would set a default for it. And then that would make it so that it could never enter a non-blocking phase, which, I don't know, good idea. Now, you could say a lot of these problems that Uber had encountered in Golang were from straying from best practices. And I'm not going to be the first to stand on stage and say, hey, large enterprises, you should write better code. But I think it kind of shows the problem that maybe if Golang or Uber themselves had kind of poked into the dining philosophers problem, would they encounter these problems still? And it's like, at Uber scale, if they would have sat down and said, hey, we're going to have 10,000 philosophers sitting at a table, would they been able to see this without having to go back and need tools like GoLeaks or pprof? Or is this something that is more indicative of like our environment? Like basically at Uber scale, they didn't really care that you were entering like a resource holding pattern because they could just buy more resources. Like when you have indefinite money, you don't really care if like half of your procs are just like hanging around. So maybe this is a problem in how Go is implementing and handling concurrency. And this is something that we could go back and like rethink our approach on what did the idioms in Go say and how can we make it more deterministic over time. So it's something to think about. And I like giving this talk and basically saying at the end that the last time I gave it, someone asked like, how can I make things faster while also keeping things correct? And I said the biggest problem is you can either choose speed or you can choose correctness. And that's like what every consistency model shows. You can either be weak and fast or you can be strong and slow. So I think I always choose to be strong and slow because I'm a back-end dev and I think you'll eventually get to the right state. But in this case, maybe it would have been better if also Uber was slow, which I don't like when my Uber Eats drivers are slow, so maybe that's not always a good thing. Anyways, I'd love to hear if you've encountered problems with concurrency at your scale or enterprises or small things that you've done. Like in my case, I've moved a timer and caused Robinhood to fall over because I just moved it up one line outside of a case statement. So I'd love to hear about that, or if you think this could have been solved other ways. Thanks. Questions? Yeah, you got 2 whole seconds. Anyone questions?
2 minutes, but okay.
If you put like pressure on them, then they'll go.
Okay. 2 seconds questions.
Yeah, 2 seconds questions, and it better be fast. Matt, have you ever encountered a problem with concurrency at your scale?
Not that I could solve myself.
Oh, that's shit. Well, cool.
There must be libraries you can use to solve some of this stuff. It's not just channels, right?
No. I mean, the thing that Uber did was they were like, yo, we're going to implement all this in CI, so it blocks developers from using like non-standard practices is probably the best way to say it, which did like cut down on like, I think it was like 70% of their problems. And they saw like a cut from like, it was, the diagrams are cool. Go look at the pictures on the talk that's there. But yeah. Anything else?